Modern road construction blends precision engineering, smart technologies, and innovative methods to build safer, faster, and more sustainable transportation networks. Road paving quality begins long before asphalt reaches the site. The transport of materials plays a critical role, as asphalt quality depends on how it is mixed, stored, and delivered. Unnecessary delays reduce material temperature and performance, directly affecting ride quality and surface finish. At the asphalt plant, storage time should be minimized, especially for surface coarse materials and polymer-modified mixes. While base and binder mixes may be stored for limited periods, surface courses should be delivered fresh whenever possible. Delivery drivers carry major responsibility for maintaining quality. Maximum journey times must be agreed, and drivers should avoid loading vehicles if delays or breaks are expected. Each load is visually inspected for issues such as uncoated aggregate or excess binder, and vehicles must be properly insulated to prevent heat loss. Poor material quality is a major cause of defects such as poor joints, inadequate compaction, fatty surfaces, and visible load marks caused by cold asphalt. Before arrival, drivers must understand site instructions, haul routes, access points, and safety rules. Vehicles prepare to tip efficiently, minimizing stoppages to keep paving continuous. Milling or planing is a critical preparatory step. A smooth, accurately planed surface ensures good bonding and prevents aggregate drag. Bond coat is then applied to guarantee adhesion between layers, and trafficking on unbroken bond coat is avoided to prevent stripping and long-term damage. High-quality paving requires well-maintained machinery and correct setup. The screed must reach proper temperature and profile before work begins. A banksman coordinates vehicle movements, especially during reversing and night operations, ensuring a steady and controlled flow of material into the paver. Continuous paving is essential as every stop can leave surface undulations. Finally, proper rolling completes the process. Joints are trapped first, rolling patterns are overlapped, and compaction is completed within temperature limits. When paving principles are followed, the result is a smooth, durable, and high-quality road surface. An asphalt paver is a key piece of equipment in modern road and commercial paving projects, responsible for placing hot mix asphalt evenly and efficiently to create a smooth, durable surface. To achieve high-quality results, every paving operation must begin with a thorough pre-paving checklist. First, the screed must be properly heated to prevent the asphalt from sticking and tearing. Operators then set the paving width, adjust the main screed crown, and configure the slope extensions to match the project requirements. The screed is lowered into the correct starting position, and the end gates are set to control the edges of the mat. In addition, the auger height is adjusted to approximately 2 inches above the thickness being placed, and the feed sensors are carefully calibrated to ensure consistent material flow. Before any hot mix asphalt is laid, a tack coat must be applied. This tack coat is an asphalt emulsion that bonds the new layer to the existing surface. The road surface must be clean and free of dust or debris, so sweeping or blowing is essential. As the emulsion breaks, the water evaporates and leaves behind asphalt, which can be identified by a color change from brown to black. Only after the tack coat is fully broken and the pre-paving checklist is complete is the crew ready to begin paving. When the asphalt truck arrives on site, the dump man safely guides it into position in front of the paver. He ensures that the hopper remains between 1/3 and 2/3 full at all times to maintain steady operation. The hot mix enters the hopper and is transported by conveyors to the auger chamber. The flow of material is regulated either by variable conveyor speed or by flow gates that strike off excess mix. Once the material reaches the augers, it is evenly distributed across the front of the screed. Maintaining a constant head of material in this area is critical, as it allows the screed to produce a uniform mat with the correct thickness and texture. The screed also maintains the proper angle of attack, which directly affects mat thickness and smoothness. After placement, a well-planned rolling pattern is established to compact the asphalt to the required density. Typically, a steel wheel roller performs the initial compaction, followed by a pneumatic or traffic roller that provides the finishing compaction and surface refinement. For commercial paving projects, such as parking lots, design and base preparation play a crucial role. The base layer can be compared to a cake, with the asphalt surface acting as the frosting. If the base is weak, poorly compacted, or cracked, the asphalt surface will quickly fail. Proper subgrade preparation, correct slope for drainage, and selecting the appropriate asphalt mix and thickness based on traffic loads and climate conditions are all essential to ensuring a long-lasting and successful pavement. At the Bluff City project, Andale Construction begins the road construction process by offloading the slurry, a mineral-based stabilizing material prepared for soil treatment. The existing dirt road is then ripped to the required depth to loosen the in-situ material and create a uniform layer before treatment. After ripping, the crew proceeds with injecting the slurry directly into the loosened soil. This is followed by thorough mixing of the native material and slurry, ensuring the binder is evenly distributed and bonds effectively with the soil particles. Once mixing is completed, the treated layer is compacted using a pad foot roller, which kneads the material and achieves deep compaction. The surface is then refined through finish blading and flat rolling, producing a smooth and level base. To verify performance, density testing is carried out to confirm that the compaction meets design specifications. Next, microcracking is performed to control shrinkage and improve flexibility before surfacing. With the base fully prepared, asphalt is paved over the stabilized layer. Finally, the surface is protected using HA5 high-density mineral bond, applied in 2 stages. The first coat penetrates and seals the surface, while the finishing coat enhances durability, dust control, and long-term performance of the roadway. The construction of the aggregate base course begins with scarifying and site clearing to remove loose soil, vegetation, and unsuitable materials, ensuring a stable foundation. After the surface is properly prepared, aggregate base course material is unloaded evenly along the road alignment. A motor grader is then used to spread the aggregate, check levels, and make necessary corrections, achieving the required thickness and cross slope. Once the desired profile is confirmed, the surface undergoes final compaction using a 10-ton roller. This compaction process increases density, improves load-bearing capacity, and creates a strong, uniform base ready for subsequent pavement layers. After the completion of earthwork, the sub-base of the road is constructed using granular sub-base material. This layer is made from well-graded granular soil that provides strength and stability to the pavement structure. The material is spread evenly and adjusted to maintain suitable moisture content before compaction. GSB is laid in layers not exceeding 200 millimeters in thickness to ensure uniform compaction. Each layer is compacted using appropriate equipment until the required density is achieved, strictly following the design and more technical specifications. Hot in-place recycling is an efficient method for rehabilitating asphalt pavements using the existing material directly on site. First, the worn road surface is uniformly heated to soften the old asphalt layer. Once the required temperature is reached, the softened asphalt is loosened by milling or scarifying, allowing it to be reworked without removal. Next, the reclaimed asphalt material is thoroughly mixed with a rejuvenating agent or additional binder to restore its flexibility and performance properties. The recycled mix is then immediately laid back onto the road surface and carefully leveled to the desired profile. Finally, the pavement is compacted using rollers to achieve proper density and surface smoothness. This entire process is typically completed in a single pass using a specialized train of equipment. As a result, hot in-place recycling significantly reduces the need for new materials, lowers construction costs, and effectively addresses common pavement distresses such as cracking and wheel rutting. The microsurfacing process begins with loading the required materials onto a specialized paving truck. Once fully loaded, the truck travels to the road section that requires surface treatment. At the site, the existing asphalt surface is cleaned to remove dust, loose particles, and debris, ensuring proper bonding of the new layer. Inside the mobile mixing unit mounted on the truck, the materials are continuously measured and mixed in precise proportions. The mixture consists of water, asphalt emulsion, very fine crushed stone aggregates, and selected chemical additives. Polymer is commonly added to the asphalt emulsion to enhance flexibility, durability, and resistance to traffic wear. The freshly mixed microsurfacing material is then immediately spread onto the pavement through a spreader box attached to the rear of the truck. The mixture is evenly distributed to form a thin, uniform layer that fills surface voids, seals minor cracks, and restores texture. After placement, the layer cures quickly through a chemical reaction, allowing the road to be reopened to traffic in a short time. The Gomeco GP2400 is a world-class slipform concrete paver built for precision and versatility in PQC paving. It can pave up to 16 feet wide with a telescoping frame or 24 feet with inserts, and is available in 2-track or 4-track configurations. Equipped with the G+ digital control system, it supports streamline or 3D guidance, ensuring accurate paving, easy mold positioning, excellent operator visibility, and efficient job-to-job mobility. The Wirtgen W200 Fi is Wirtgen's latest large cold milling machine, designed to maximize productivity and reduce operating costs through intelligent technology. Powered by a 610 HP Cummins QSX15 engine, it offers a 2,000 mm milling width and up to 330 mm cutting depth. Advanced systems such as Mill Assist, Level Pro Active, Performance Tracker, and the Quick Change Milling Drum System ensure high efficiency, precision, and flexibility on demanding road projects. Hot asphalt paving uses specialized pavers and crews to spread heated asphalt mixture, forming smooth, durable road surfaces efficiently nationwide. The entire parking lot is resurfaced with asphalt. First, a wheel loader clears snow from the area to prepare the surface. Dump trucks then deliver asphalt material and unload it onto the ground. An asphalt paver, supported by workers, spreads the hot mix evenly, while a wheel loader feeds material into the paver's hopper. Damaged sections are broken and removed by an excavator. Immediately after paving, a road roller compacts and smooths the surface to achieve a flat, durable finish. The process begins with hot asphalt being dumped directly along the edge of the roadway, forming an initial supply of material for the shoulder construction. This asphalt is positioned in advance to ensure a continuous and uninterrupted paving operation. Next, the roadside asphalt paver moves forward along the road edge. The machine is equipped with a long side screed mounted on the side, which operates parallel to the roadway. As the paver advances, the side screed continuously spreads and levels the asphalt along the shoulder area. This setup allows the material to be placed precisely at the required width and thickness while maintaining a consistent alignment with the main pavement. During the paving operation, the side screed smooths the asphalt surface and provides initial compaction, creating a stable base layer along the road edge. The continuous movement of the machine ensures that the shoulder is formed evenly without interruptions or surface irregularities. Immediately behind the paver, workers manually distribute additional asphalt concrete material onto the freshly paved shoulder. This manual spreading helps fill edges, correct minor surface imperfections, and ensure proper bonding between layers. The workers carefully adjust the material to achieve a uniform profile and clean transition between the roadway and the shoulder. After the material is evenly distributed, the shoulder is ready for further compaction and finishing in subsequent steps, ensuring a durable and well-formed rigid roadside shoulder. The in-situ concrete barrier is a permanent vehicle restraint system designed for use on roads and highways, providing high levels of safety and durability. In accordance with current regulations, this system must comply with essential requirements such as CE marking and achieving an approved ASI severity index. Compared with other vehicle containment systems, in-situ concrete barriers offer several significant advantages. These include a lower life cycle cost for high containment applications, very low or zero deformation during impact, minimal occupation of the roadway platform, and excellent vehicle redirection performance. In addition, the system operates independently of the base soil conditions on which it is installed. GIVASA offers 5 types of high-containment in-situ concrete barriers. The lightest model in the range is designed for single-face impact and is suitable for any stable ground where horizontal load should not be transmitted to the foundation. This barrier features the smallest working width currently available, making it ideal for locations requiring zero displacement and reduced maintenance costs, while allowing the attachment of elements such as planters on the rear face. Other models are designed for central medians with limited space, double-sided impacts, or varying height differences up to 750 millimeters. Through these innovative solutions, GIVASA continues to advance road safety, placing user protection as its highest priority. Borum is one of the world's leading suppliers of professional self-propelled line marking machines and equipment. By offering solutions for thermoplastic, cold paint, and two-component applications, Borum is able to meet almost every road marking requirement. As a result, its machines are widely used in cities, on main roads and highways, as well as at airports around the world. Firstly, the BM2000 is the smallest and most agile model in the Borum range. Thanks to its compact design and excellent maneuverability, it is especially suitable for urban environments, smaller roads, and airport marking. Moreover, it can be equipped for airless cold paint application, which is commonly required at airports due to its ability to produce sharp and precise lines. In addition, the machine can be configured with either two 220-liter tanks for dual-color marking or one 440-liter tank for single-color use, making it a flexible solution for varied tasks. Next, the BM2500 and BM2700 are designed for small to medium-sized projects. While the BM2500 offers a slidable operator seat that allows comfortable operation on both sides of the road, the BM2700 introduces redesigned glass bead tanks that make refilling easier and faster. Consequently, both machines perform efficiently in city areas, on main roads, and in hilly terrain, combining agility with good load capacity. For larger projects, the BM3000 provides higher material capacity and faster application speed. Therefore, it is well suited for major urban jobs, highways, and larger airport areas. It can be equipped with two 440-liter tanks for dual-color marking or one tank for single-color application, reducing the need for frequent refilling. Furthermore, the BM5000 and BM5500 represent Borum's high-end solutions. These machines are designed for large-scale projects such as highways, motorways, and airport runways. With maximum capacity, powerful performance, and the ability to operate in demanding conditions, including high temperatures up to 50 degrees Celsius, they ensure continuous and efficient workdays with minimal interruptions. In comparison with hand-pushed machines, self-propelled Borum machines are significantly more efficient. For example, the BM2000 can complete a long marking stretch almost 4 times faster than a hand-guided machine, while also delivering higher precision. Therefore, especially under tight deadlines and in busy airport environments, self-propelled line marking machines are clearly the superior choice. In conclusion, Borum offers a complete range of self-propelled line marking machines that combine precision, efficiency, and reliability. Whether used in cities, on highways, or at airports, these machines provide contractors with optimal performance and long-term value. First, the damaged area is cleaned to remove loose debris and ensure good bonding. Once the surface is prepared, the fast-patch polymer-based repair material is poured directly onto the cracked asphalt. The material has a thick consistency, allowing it to fill deep cracks and low spots easily. Using a squeegee, the operator spreads the mixture across the surface. The thickness can be adjusted as needed. It can be pulled tight for thin applications or spread thicker where the pavement has settled or deteriorated more severely.
Whatever thickness you need, really. I mean, it's designed to pull really tight. See how where he's going thin with it?
Use it like a slurry.
Exactly.
First, the damaged area is cleaned to remove loose debris and ensure good bonding. Once the surface is prepared, the fast patch polymer-based repair material is poured directly onto the cracked asphalt. The material has a thick consistency, allowing it to fill deep cracks and low spots easily. Using a squeegee, the operator spreads the mixture across the surface. The thickness can be adjusted as needed. It can be pulled tight for thin applications, or spread thicker where the pavement has settled or deteriorated more severely.
But see how thin you can go with it. That's what it's designed to do.
Now how about shrinking?
None. It's a polymer. What I would do, Harley, because we have one kid, I'd take that excess material and take it down towards your truck.
If excess material remains, it can be pulled away and redistributed to other damaged sections, minimizing waste. Overall, the Fast Patch ACR kit is designed for durability, ease of application, and efficient repair of alligator cracking, restoring the asphalt surface quickly and effectively. In modern multi-story steel building construction, column splicing plays a vital role in extending the height of structural columns. A column splice is a structural connection that joins two separate column segments to form a continuous load-bearing member. Because steel columns are fabricated and transported in limited lengths, they must be assembled on site in stages. Therefore, column splicing becomes an essential solution that allows tall buildings to be constructed efficiently and safely.
I'm gonna have you going home cussing tonight. What the hell got into you, Jim?
To begin with, the primary purpose of a column splice is to extend the column length while maintaining structural continuity. By connecting individual sections, the splice ensures that the column behaves as a single element capable of transferring loads from the upper stories down to the foundation. As a result, the building frame maintains a continuous load path, which is critical for both gravity and lateral load resistance. Without proper splicing, the structural performance of the entire building would be compromised.
Closing gap.
Among the different splicing methods available, bolted column splices are the most commonly used in on-site construction. This is mainly because bolted connections are easier to install, faster to assemble, and simpler to inspect compared to welded splices. In addition, bolted splices are less affected by weather conditions and do not require highly specialized equipment on site. Consequently, they offer greater flexibility and reliability during the erection process. In a typical bolted splice, the connection is formed using steel plates and high-strength bolts. More specifically, flange plates are attached to the flanges of I-shaped or H-shaped columns to transfer axial loads and bending moments. At the same time, web splice plates or cover plates are connected to the web of the column to transfer shear forces. Through this combination of plates and bolts, all internal forces acting on the column are safely transmitted across the splice. Moreover, when the bolts are properly tightened, sufficient clamping force is generated, which enhances friction and improves the overall strength of the connection. Furthermore, the design of bolted column splices requires careful consideration of load transfer and splice location. The splice must be capable of resisting axial forces, major and minor axis bending moments, and shear forces. For this reason, engineers carefully select bolt sizes, plate thicknesses, and bolt arrangements. In addition, splices are typically located near floor levels, where beams and slabs provide lateral restraint. This placement reduces bending demands on the splice itself and improves structural stability. Equally important is the consideration of seismic performance. In earthquake-prone regions, bolted column splices must comply with seismic design requirements, such as minimum shear capacity and proper detailing to ensure ductile behavior. These measures allow the structure to absorb and dissipate seismic energy without sudden failure. In conclusion, bolted column splicing is a fundamental technique in steel building construction. By using steel plates and high-strength bolts, this method ensures structural continuity, efficient load transfer, and safe erection of multi-story buildings. Ultimately, bolted splices enable steel columns to rise seamlessly from one floor to the next, forming a stable and reliable structural framework. The construction of the steel structure for the Walterdale Bridge involved a highly controlled sequence of fabrication, assembly, transportation, and final installation. The central steel arch, weighing approximately 1,000 tons, was fabricated and assembled on land near the riverbank. Over several months, iron workers carried out extensive welding, bolting, and alignment work to ensure the structure met precise engineering tolerances before any movement took place. Once the arch assembly was complete, attention shifted to preparing the temporary steel support system known as red iron. This red-painted falsework was erected to support the bridge during the lifting and positioning stages. Iron workers installed vertical columns, diagonal braces, and horizontal beams, carefully connecting each element using high-strength bolts and field welds. Every connection was checked repeatedly, as even a minor misalignment at the base could result in significant deviation at the top of the arch. With the red iron structure in place, iron workers installed bracing components that would temporarily bear the weight of the arch during transport. These braces were connected at height, requiring workers to maneuver across narrow steel members while securing bolts and tightening connections under icy conditions. The temporary system was locked into position to prevent any movement once the arch began to shift. Before the steel arch could be moved, two barges were positioned beneath the structure. Iron workers worked alongside marine crews to align the barges precisely under the skid shoe system. The skid shoes, installed at the base of the arch, were greased to allow the structure to slide smoothly. Winches and cables were attached, and all load paths were inspected to ensure the weight transfer would occur evenly. As the sliding operation began, the arch was slowly pushed from land onto the barges. Iron workers monitored the movement from multiple points, checking clearances and ensuring the structure remained stable. The operation proceeded at a controlled pace, as the slightest imbalance could cause the arch to bind or shift unexpectedly. Once fully supported by the barges, the arch was secured with temporary restraints to prevent lateral movement. The next phase involved floating the steel arch upstream to its final location between the bridge towers. Throughout this process, iron workers remained on standby to address any adjustments required during transport. The barges were winched forward in small increments, while workers continuously inspected the steel connections, skid shoes, and temporary supports. Upon reaching the installation site, the barges were positioned beneath the permanent support towers. Iron workers then prepared the final landing points by installing and modifying the permanent skid shoes on the south shore. These steel components were critical, as they would receive the full load of the arch once it was set into place. The installation had to be completed before the arch arrived, leaving no margin for delay. As the arch approached its final position, ironworkers guided it into alignment using winches and controlled cable tension. Communication between crews on the barges, onshore, and on the towers was constant. The structure was slowly maneuvered between the two towers, with alignment checks performed repeatedly to confirm that the arch matched the engineered position. When the arch was correctly aligned, it was carefully lowered onto the permanent skid shoes. This step required precise coordination, as the full weight of the steel structure transitioned from the barges to the bridge supports. Once seated, ironworkers immediately began securing the arch by tightening high-strength bolts and installing temporary welds to lock the structure in place. With the arch supported by the towers, ironworkers proceeded to remove selected bolts and temporary connections from the red iron falsework. Welders followed, completing full penetration welds at critical joints to permanently fix the arch to the bridge structure. Each weld was performed according to strict specifications and inspected to ensure structural integrity. After the main arch was secured, the remaining temporary steel supports were dismantled in stages. Ironworkers unbolted braces, removed columns, and lowered steel components safely to the ground. This process was carefully sequenced to maintain structural stability throughout the removal of the falsework. The final phase of the steel structure construction involved detailed inspections, final tightening of all bolted connections, and completion of remaining welds. Ironworkers verified alignment, checked load paths, and ensured that the steel framework met all design requirements. Once all connections were confirmed, the steel arch became a permanent, self-supporting element of the bridge. Through a combination of precision fabrication, controlled movement, and expert steel erection, the ironworkers successfully completed the most complex phase of the bridge's construction. The finished steel structure stood fully integrated into the bridge system, ready for the next stages of construction. The installation of reinforced concrete pipe begins with careful preparation around the manhole area. In this project, the manhole required multiple adjustments because the pipe needed to fit precisely. The team had to remove sections and notch the base of the manhole twice to allow the pipe to pass through. This initial step is critical, as it ensures that the pipe aligns correctly with existing structures. Once the adjustments were completed, the team established reference points for the catch basin. Stakes were placed at the bottom of the excavation, indicating where the catch basin would be positioned. The catch basin, a square concrete structure designed to collect and direct water flow, was placed in front of the excavation area. To maintain accuracy, offsets were checked and stone grades were recalculated. These measurements ensured the catch basin and pipe run would be installed at the correct elevation. Next, the trench for the pipe run was dug with precision. Since the catch basin occupied a large portion of the hole, the excavation was adjusted to balance the elevation. Soil was removed and repositioned to allow the pipe to sit near grade level. Although perfect leveling was not necessary, consistency was key to achieving proper flow. The trench was shaped to gradually rise toward the next catch basin, creating a slope that would allow water to flow efficiently through the system. The team paid close attention to detail, making small adjustments as needed to maintain a proper line of elevation. A fundamental concept in reinforced concrete pipe installation is the invert. The invert refers to the lowest internal point of the pipe, essentially the water line or flow line. To ensure a proper slope between two catch basins, the team calculated the difference in invert elevations. In this case, after accounting for the thickness of the pipe, the total rise was determined to be 0.84 feet over a 28-foot run, producing a 3% slope. For field implementation, this was converted into a simpler measurement. Every 10 feet of horizontal distance required a rise of 0.3 of a foot. This practical approach allowed the team to check slope without specialized equipment like a pipe laser. Ryan, the crew member responsible for checking grades, confirmed that the trench matched the calculated slope before any pipe sections were installed. Pipe sections were then prepared and positioned in the trench. Full-length pipes were not suitable for this run, so custom-cut pieces were used. These cut pieces were chosen to avoid ending the run with a very short section, making installation easier and more efficient. Positioning these pipes required careful alignment at both bell and spigot ends. Occasionally, bricks or temporary supports were used to provide resistance while seating the pipes. Each section had to be aligned precisely with reference stakes, maintaining the slope and ensuring smooth water flow. Crew members worked together, lifting and adjusting each pipe until it was properly seated in the trench. Once the pipes were in place, attention turned to installing the catch basin. Layouts were marked, plumbing was aligned to reference stakes, and the base was set. Specialized catch basin keys were used to secure the structure in place. Throughout this stage, compacted soil was adjusted and redistributed to support the pipe and maintain the slope. The crew continuously verified the alignment, invert, and grade of each component. Proper installation required coordination, communication, and careful adjustment at every step. After the catch basin was secured and the pipe run correctly sloped, the system was ready for final inspection. This meticulous process, from adjusting the manhole to trench excavation, slope calculation, pipe cutting, positioning, and catch basin installation, demonstrated the integration of engineering calculations with practical fieldwork. Attention to detail at every stage ensured a durable, functional drainage system. Each element was carefully aligned and verified to maintain proper flow and structural integrity, resulting in a well-executed reinforced concrete pipe installation project.